Hi everybody, this is Bayesion, an undergraduate student in Tianjin University. It's my pleasure to represent our recent work on compiler autotuning. This work has done by Tianjin University and the University of Newcastle together, and now I'll get straight to the point. Compiler transforms a source program written in certain programming language into an executable program. A typical compiler GCC supports a large number of optimization flags. All the optimization flags can be enabled or disabled for tuning to achieve certain runtime performance. However, the large number of flags forms a huge configuration space. It is challenging for users to understand all the flags to manually tune a compiler. So compiler developers predefine several optimization levels. It is not a guarantee to achieve the required runtime performance. So we focus on the problem of compiler autotuning. In our work, we tune all the optimization flags automatically to optimize the compilation and execution time for the given programs. The challenge of compiler autotuning is to deal with the efficiency problem. Our research on the approaches in the area of compiler autotuning show that the state-of-the-art approaches in this field takes too long to achieve a good performance, because exponential flag combination forms a large space for searching. Therefore, with a large number of flag combinations to compile and execute, those approaches cannot achieve certain speedup within the given time. So we propose a Bayesian optimization-based approach to improve the efficiency of compiler autotuning. Well, some Bayesian optimization-based approaches also have efficiency issues when facing high-dimensional data. The reasons are twofold. In the first step of Bayesian optimization, Gaussian process model cannot scale to high-dimensional data, and then the second model will need to make prediction for all flags combinations, so it takes too long to complete even one iteration. Based on those, we propose the first Bayesian optimization-based approach for compiler autotuning, called BOCA, and address the limitation of the traditional Bayesian optimization. So the process for BOCA is, first we build a surrogate model of the objective functions that we're going to optimizing. The surrogate model makes prediction for all settings in candidate optimization sets. And then we're going to have these candidate optimization sets. Here is a novel selection strategy we designed. It is kind of the same as the heart of the BOCA. In each iteration, it chooses a subset from unevaluated flag combinations as a candidate set. And we'll talk about how our selection strategy works later. Then an acquisition function. It told what is the point I should evaluate next. BOCA compiled and executes the best settings, added to the training set, and update our surrogate model. So this is how BOCA designed the policy for the optimizing process. The rest of the optimization loops follows quite naturally from this. BOCA repeats this process ad infinitum until the amount of given iteration just elapses. And finally, BOCA will output an optimal settings as its recommendation. Now we sort of take a high-level overview of BOCA. As is shown in the figure, the two primary contributions in BOCA are: we propose a first Bayesian optimization-based approach to improve the efficiency of compiler autotuning. And then we design a novel selection strategy to further improve the efficiency of BOCA. We'll talk about the modeling in Bayesian optimization process in detail. What the things you actually need to build a surrogate model are a training set and the mechanism for modeling. So the first step. For BOCA, and training instance is a flag combination and the corresponding execution and the compilation time energy settings for the given program. The initial training data are sampled randomly from configuration space, and later in each iteration, BOCA selects the best settings, evaluates it, add the training instance to update our surrogate model. And for the second step, we use random forest to train the surrogate model. We replace Gaussian process in traditional Bayesian optimization because random forest can scale to high-dimensional data in our problem. And in the next step, the random forest model makes prediction for each candidate flag combinations. and will output their mean and standard deviation to compute expected improvement as acquisition function. BOCA uses EI to decide where to sample next because EI considering both exploration and exploitation. After having this random forest model to guide sampling, we further design a novel selection strategy to choose a subset from unevaluated flag combinations as a candidate set for the model to make prediction for. Our selection strategy makes a balance between exploitation and exploration. For exploitation, our selection strategy takes advantage of random forest model. In each iteration, it computes the impact of all flags, and the top K are identified as impactful optimization. The rest of the optimizations are identified as less impactful. BOCA will exploit all combinations of impactful flags because we assume that by fully exploiting impactful flags, we can find a desired flag combinations more efficient. Well, a complete optimization settings need both impactful and less impactful flags. And also there can be noise when deciding which flags are impactful. And exploiting less impactful flags is also necessary. BOCA explores some randomly sampled less impactful flags combinations with decay. And with the known area getting bigger, BOCA will explore less number of less impactful flags combinations to further improve the efficiency. A decay function is used to decide how many number of less impactful flags combinations we are going to explore at each iteration. About our evaluation, we evaluated BOCA on two most popular C compilers, GCC and LLVM. We use two widely used C benchmarks, cBench and PolyBench. We select 10 programs from each benchmarks respectively, and here the indicator we use to measure the effectiveness of BOCA. We define the speedup as the compilation and execution time speedup over O3. We compare with other approaches in terms of time spent on achieving certain speedups. The speedup setting we use including the speedup achieved by BOCA on its 30th, 40th, 50th, and 60th iteration. Here we illustrated the effectiveness of BOCA. We first show that BOCA can outperform O3 in its 6 iterations on both GCC and LLVM across all 20 selected programs. In RQ1, we compare BOCA with existing compile autotuning approaches that are listed on the right of the slide. The results show that BOCA outperforms all the approaches in each settings. The average improvement ranged from 42% to 78%. We further compared our selection strategy with local selection strategy in SMAC, denoted as BOCA-S. The Bayesian graph shows that the average time spent by BOCA is shorter than BOCA-S. The average improvement of BOCA over BOCA-S are 42% on GCC and 36% on LLVM. We further investigated whether the decay process worked. We compared BOCA with its variant with no decay, denoted as BOCA no decay. Here's the result. It shows BOCA indeed takes less time to achieve the same speedup in all the settings, demonstrating the contribution of the decay process. In the presentation, we propose first Bayesian optimization-based approach for efficiency compiler autotuning. We design a novel selection strategy to further improve the efficiency of BOCA. We compare BOCA with 3 existing compiler autotuning approaches and with 3 Bayesian optimization-based methods, and the result indicates the effectiveness of BOCA in compiler autotuning. Thanks for listening.
Hi, welcome everybody to this Q&A part. We are in the session programming general issues. This is here Gregorio Robles from the Universidad Rey Juan Carlos in Madrid, Spain. And the Q&A now is on paper efficient compiler autotuning via Bayesian optimization, which has been done by colleagues from the College of Intelligence of Computing in Tanging University and the University of Newcastle. So we've got the pleasure here to have Peiki who will be answering your questions. So as you already know, if you have any question, you have the chat on that part where you can post your questions, and I will read them aloud, and Becky will answer the questions as good as she can. So in the meantime, while you're writing your questions, I have here some questions that I would like to ask the authors. So you've done a very nice method, which you call BOCA. Is it available as a tool for others to use it?
What?
Yeah, I mean, is BOCA what you call BOCA? Have you done it a tool so that other people can use it as a tool, or is it just what you call BOCA? Is it just a method that you have applied on your own and you haven't released it?
You mean why we named our paper BOCA?
No, not why is if BOCA is, I mean, BOCA is a tool. I guess you have created some implementation and and did some code writing. Is it available for other researchers?
Yes, we published our code on the GitHub, and we documented our technique very well, because there are some techniques that a little hard to understand, because it involves in compilation and execution of a program. We documented it, and you can also find the data and our experiment result on our web page too.
Okay, so in the paper, no, you refer to the paper to those who want to see the GitHub page of BOCA. Okay, so we have a first question here from Alex. He's asking, have you compared the speed up you are able to achieve with BOCA to those achievable with profile-guided optimization?
To what optimization?
Profile-guided optimization. So you can read it in the chat.
Have you compared the speed up that you're able to achieve with those achieved with profile guided optimization?
Mm-hmm.
I don't understand what is profile guided optimization.
That's another technique. So I guess then the answer here is you haven't compared it. So after each Q&A session there is a discussion room. Maybe
Discussion.
you can talk with Alex about it, and he can guide you a little bit about how this profile guided optimization works, and you can use it for your next research. So
Okay,
there is So there is Tim as well asking. He's fascinated by the decay function, and he doesn't know where it comes from. Does this decay function come from signal processing?
The decay process is just a function we use, and it is.
So what Tim wants to know is where did you have the inspiration from the decay? Is it on your own, or where have you seen it before?
It is because our approach need to improve the efficiency. So we think about a decay function maybe help, and we look some approach with and see how they do their decay, and we choose this function as our decay function.
Okay, and what the specific question is, why specifically this decay function and not one of the many others that exist? Why have you chosen decay?
Because this decay function, at first it's like a curve that first it decays slow and will decay fast. It suits our method because in the first we need to explore a lot of the say starting space to decide, because we cannot precious decide which flags are more important. So we need to decay slow. But when our target model get more trained data, we can precious define which optimization are more impactful. So we can explore less optimization. So we can decay fast. So we choose a curve like this.
Mm-hmm. Okay, and then you've got the idea from the decay function from other works in the research literature?
Yes, it is from the relative work.
Okay. So thank you. So Tim has many other questions and comments here if you see in the chat. So one of them is if you tried random forests of different sizes.
Why didn't you try different sizes? We just follow the previous work. We saw that random forest can get an efficient model use just a little training, small training data. We use the random forest like we don't limit the max depth of the random forest. So to get an effective model, we just let the random forest use the default parameters, and we do not limit the max depths.
Okay, so I think here the other question is, so if Flash uses one tree and BOCA uses n trees, did you try two n trees? You didn't.
No,
you didn't. You just used the standard parameterized number, and then you use the same number throughout the whole research.
Yes, and we'll add it to our future work. Thank you very much.
Okay, so thank you. Yeah, so regarding future work, what would be the next steps in your research?
First, like Tim said, I will investigate about our random forest models, and we can develop can explore our method on recent version of compiler. Because recent version of compilers they are improved very well. So the just use the default provided optimization O3 is good enough, but there are still a little room for us to improve. And we are aiming to the higher version of compiler in our future work.
Okay, so here Tim says beyond compilers, much fairness research optimizes learners to avoid biases. No? And yeah, that your tech could kill that process. What do you think about that? Let's hear.
Much fairness researchers optimizing learners. To avoid biases.
Well, anyway, I mean we're getting out of time. We still have just 20 seconds. Remember, especially for Tim, who has showed much interest, there's gonna be a discussion room now specifically for this paper. It will pop up close to the chat. So I guess Decay would like to join as well, that discussion room, and then you can talk there with open video and so on.
No,